What if I told you a backyard mechanic with a piece of scrap aluminum embarrassed General Motors' entire engineering department? Not with some million-dollar prototype or sophisticated computer modeling, but with a modification so simple that GM's top engineers literally laughed when they first saw it. This is the story of how one small-town racer discovered something GM's best minds had overlooked, and how his homemade $20 part would quietly revolutionize the way Detroit thought about engine design. Picture this. It's 1987 in Lebanon, Tennessee, and the Saturday night races at Highland Rim Speedway are about to start. The air is thick with tire smoke and the smell of high-octane fuel. In the pits, surrounded by gleaming professional race cars with corporate sponsors and factory support, sits a primer gray Chevrolet Monte Carlo that looks like it barely survived a demolition derby. Behind the wheel is Tommy Big Red Morrison, a 42-year-old machinist who works 60 hours a week at the local tool and die shop. His entire racing budget for the season? $3,000. The GM factory team spending that much on catering for a single race weekend are about to get schooled. This isn't just another David versus Goliath racing story. This is about what happens when real-world experience collides with theoretical engineering, when a man who understands airflow from feeling it with his hands proves that sometimes the best innovations come from the people actually turning wrenches, not the ones running computer simulations in climate-controlled laboratories. Tommy Morrison didn't just beat GM's factory-backed teams on the track, he exposed a fundamental flaw in how Detroit had been thinking about engine design for decades. To understand why Morrison's discovery was so significant, we need to travel back to the muscle car era of the 1960s. General Motors dominated American motorsports with their big block V8 engines. The formula was simple: displacement equals power. Want more horses? Build a bigger engine. The 396, the 427, the legendary 454. These were brute force solutions to a physics problem. But by the early 1980s, everything had changed. Fuel economy standards, emissions regulations, and insurance costs had killed the big block era. GM's engineers were now trying to squeeze every possible horsepower from smaller engines, and they thought they had it figured out. The small block Chevrolet V8 was GM's crown jewel. First introduced in 1955, it had been refined and perfected over 3 decades. By 1987, GM's engineers were confident they understood every aspect of this engine. They had wind tunnels, flow benches, and the first generation of computer-aided design systems. They had PhDs in fluid dynamics and thermodynamics. They had million-dollar testing facilities where they could measure airflow down to the cubic centimeter. What they didn't have was Tommy Morrison's 30 years of experience listening to engines tell him what they needed. Morrison had been racing since he was 16, starting with a 1955 Chevy his father helped him build in their barn. He never went to engineering school. Hell, he barely finished high school. But he understood engines the way a musician understands instruments, by sound, by feel, by instinct, developed over thousands of hours of trial and error. And in 1987, he was struggling with a problem that would lead to his breakthrough. The issue was throttle response. Morrison was running a built 350 cubic inch small block, pretty standard for the street stock class at Highland Rim. The engine made decent power, about 385 horsepower on the shop's ancient dyno. But coming out of the track's tight turns, there was a dead spot. Push the throttle at corner exit, and for a fraction of a second, nothing happened. Then the power would hit all at once, breaking the rear tires loose. In a 16-lap feature race, those fractions of seconds added up. The factory-backed cars with their precisely tuned engines didn't have this problem. Morrison spent weeks trying everything: different carburetors, various cam profiles, every ignition timing curve he could think of. Nothing solved the bog. Then one night, after another frustrating fourth-place finish, he was staring at his engine in the garage when he noticed something. The intake manifold The aluminum casting that distributes the air-fuel mixture to each cylinder sat directly on top of the engine block. The carburetor bolted to the top of the manifold. Between them, about 4 inches of aluminum separated the carburetor from the cylinder heads. But here's where it gets interesting. Morrison had spent his day job machining parts for industrial air compressors. He understood that when air moves through a passage and suddenly has to change direction, it creates turbulence. Turbulence means inefficiency. Looking at his intake manifold, he could visualize the air-fuel mixture coming down through the carburetor, hitting the floor of the manifold plenum, and having to make a 90-degree turn to enter the runners, leading to each cylinder. That impact and direction change had to be causing problems. The solution came to him at 2 in the morning. What if he could give the air-fuel mixture more space to make that turn, more room to organize itself before entering the runners? He sketched his idea on a napkin, a spacer between the carburetor and intake manifold. Not just any spacer, but one with a carefully designed internal profile that would smooth the airflow transition. The next day, Morrison took a chunk of aluminum billet to work. During his lunch break and after hours, using the shop's old Bridgeport mill, he machined his first spacer. It was 1 inch tall with a 4-hole design matching his carburetor's butterfly pattern. But instead of straight holes, Morrison created a complex internal taper. The top matched the carburetor openings, then gradually expanded into an open plenum area before smoothly transitioning to match the intake manifold opening. He called it a transition spacer. That Saturday night at Highland Rim, Morrison bolted his homemade spacer onto the engine. The first thing he noticed was the sound. The engine's idle note had changed, deeper, smoother. On the track, the difference was immediate. The bog was gone. Coming out of turn 2, he could roll into the throttle progressively without that dead spot. The power delivery was linear, predictable. He won his heat race by 3 car lengths. In the feature, he finished second, his best result all season. But Morrison wasn't satisfied with second place. Back in his garage, he refined the design. Using modeling clay and hours of patient shaping, he created what he thought was the ideal internal profile. Then he machined version 2. This one was 1.25 inches tall, with an even more complex internal geometry. The transition from the 4 carburetor holes to the open plenum followed a mathematical curve Morrison had worked out on paper, not using formulas he'd learned in school, but ratios he'd discovered through trial and error. The second version was even better. But it was the third iteration that changed everything. Morrison added what he called velocity stacks, small trumpet-shaped protrusions inside the spacer that extended slightly into the airflow path. In his mind, these would help organize the air-fuel mixture into coherent streams. He had no way to test this theory except on the track. Labor Day weekend, 1987, the Highland Rim Speedway Season Championship, 100-lap feature race, $5,000 purse. The factory teams were there in force. Gary Sheffield from Sheffield Racing had brought 2 cars with engines built by GM Performance Parts. Bobby Allison's son Davey was there with a car prepared by his father's NASCAR Cup team. Morrison pulled into the pits with his primer gray Monte Carlo and his homemade spacer. During tech inspection, the GM factory rep, a young engineer named Michael Strasser, saw Morrison's spacer. "What the hell is that thing?" he asked. Morrison explained his theory about airflow transition. Strasser actually laughed. "We've tested every possible intake configuration on our flow benches," he said. "If spacers worked, don't you think we'd be using them?" Morrison just shrugged. "Guess we'll find out tonight." Qualifying told the story. Morrison turned a 14.832-second lap, track record. Sheffield's factory cars, 14.961 and 14.988. In racing, a tenth of a second is an eternity. Strasser stopped laughing. The race was a masterclass in consistency. While other drivers fought wheel-to-wheel battles, Morrison ran his line lap after lap. His times varied by less than 0.02 of a second. The factory cars, with their sophisticated engine management systems, couldn't match his consistency. Morrison won by half a straightaway. In victory lane, Sheffield's crew chief asked to look at the spacer. Morrison let him. "It's just a chunk of aluminum," the crew chief said. "There's got to be something else." But there wasn't anything else. Morrison's engine was actually less sophisticated than the factory units. He was running a used Holley 750 carburetor he'd bought at a swap meet. His camshaft was a mild street grind, nothing radical. His cylinder heads were stock iron units with a basic valve job. The only difference was that 1¼ inch piece of aluminum between the carburetor and intake manifold. Word spread through the regional racing community. Other racers started asking Morrison to make spacers for them. He obliged, charging $50 each, just enough to cover materials and his time. Every one of them saw improvements. Not massive horsepower gains on the dyno, but something more valuable: drivability, throttle response, consistency, the things that actually win races. Here's where the story takes an interesting turn. 3 months after Morrison's championship win, Michael Strasser showed up at Morrison's garage, not with a corporate lawyer or a job offer, but with a request. Could Morrison make him a few spacers for testing purposes? Morrison made him 6, each with slightly different internal configurations. Strasser paid cash and made Morrison promise not to tell anyone about the transaction. What Morrison didn't know was that Strasser had gone back to GM's powertrain division with data from Highland Rim. The factory car's onboard telemetry had recorded something unusual. Morrison's car showed lower intake manifold vacuum readings at part throttle, suggesting better cylinder filling. It also showed more consistent exhaust gas temperatures across all cylinders, indicating better mixture distribution. These were improvements GM's engineers hadn't even been looking for because they always tested at wide-open throttle on the dyno. Inside GM's Warren, Michigan Tech Center, Strasser set up a series of tests that would vindicate Morrison's backyard engineering. Using GM's state-of-the-art flow bench, they tested intake manifolds with and without spacers. At wide-open throttle, the difference was minimal, maybe 2 or 3 CFM of airflow. But at part throttle, between 25 and 75% opening, the spacers showed significant improvements. The air-fuel mixture entered the runners more evenly distributed. Wet flow testing, where they could actually see the fuel droplets, showed the mixture staying better suspended instead of puddling on the manifold floor. The real shock came from the transient response testing. GM had a specialized rig that could simulate rapid throttle changes. With Morrison's spacer design, the engine responded 37% faster to throttle inputs. The bog that Morrison had eliminated wasn't imagination. It was measurable, repeatable, and significant. The spacer gave the air-fuel mixture room to expand and organize before being distributed to the cylinders. It was like the difference between pouring water through a funnel versus dumping it straight down a pipe. But GM couldn't just start selling spacers. It would be admitting their intake manifold designs were flawed. Instead, something more subtle happened. Look at a 1988 GM Performance Parts intake manifold compared to a 1987. The plenum volume is 20% larger. The transition from the carburetor pad to the plenum is smoother. They essentially incorporated Morrison's spacer concept into the casting itself. The official explanation? Continued development and refinement. Morrison's name appeared nowhere in the documentation. The technical deep dive reveals why Morrison's discovery was so significant. In a naturally aspirated engine, the intake stroke creates a vacuum that pulls the air-fuel mixture from the carburetor through the intake manifold and into the cylinder. This isn't a smooth, continuous flow. It's a series of pulses, one for each cylinder's intake stroke. At 3,000 RPM, That's 12,500 pulses per minute. These pulses create pressure waves that bounce back and forth in the intake manifold. Engineers call this phenomenon reversion. Morrison's spacer acted as an accumulator, a small reservoir where these pressure waves could dissipate. The air-fuel mixture had space to stabilize before entering the runners. Think of it like the difference between drinking through a straw versus drinking through a straw with a small chamber in the middle. The flow becomes smoother, more consistent. Morrison didn't know the physics terms, but he understood the principle. The velocity stacks Morrison added in version 3 were even more sophisticated than he realized. These trumpet-shaped protrusions created what engineers call a boundary layer effect. As the air-fuel mixture flowed past them, it formed organized vortices that actually helped keep the fuel droplets in suspension. GM's later testing found this improved fuel distribution to the cylinders by 12%. Some cylinders had been running slightly rich, while others ran lean. Morrison's spacer evened this out, improving both power and fuel economy. The four-hole design was crucial, too. Morrison had matched it to his carburetor's butterfly pattern, but the effect went deeper. Each hole created its own airflow stream. These streams would collide and mix in the open plenum area of the spacer, creating turbulence that helped atomize the fuel. Better atomization meant more complete combustion. More complete combustion meant more power and cleaner emissions. GM's engineers had been trying to achieve this with complex intake manifold runners. Morrison did it with a simple aluminum block. Temperature was another factor Morrison hadn't considered, but GM's testing revealed. The aluminum spacer acted as a heat barrier between the hot intake manifold and the carburetor. Cooler air is denser, meaning more oxygen molecules per cubic foot. GM's testing showed the spacer reduced carburetor temperature by an average of 18 degrees Fahrenheit. That translated to a 2% increase in air density, worth about 6 horsepower, on a 350 cubic inch engine. The manufacturing process Morrison used also contributed to his success. By machining the spacer from billet aluminum, he created perfectly smooth internal surfaces. Cast intake manifolds, even good ones, have slight surface irregularities from the casting process. These create microscopic turbulence that disrupts airflow. Morrison's mirror-smooth machined surfaces eliminated this. It was like the difference between water flowing through a rough concrete pipe versus polished glass. But the real genius of Morrison's design was its simplicity. No moving parts, no complex electronics, no exotic materials, just a carefully shaped piece of aluminum that solved multiple problems simultaneously. It improved throttle response, increased part throttle efficiency, evened out cylinder-to-cylinder distribution, reduced fuel puddling, lowered intake temperatures, and cost less than $50 to manufacture. In engineering terms, it was elegant. The immediate impact in the racing world was dramatic. Within a year, every serious Saturday night racer was running some type of carburetor spacer. Companies like Wilson Manifolds and HVH started producing CNC machined spacers based on Morrison's concepts. The tapered four-hole design became an industry standard. Racing parts catalogs that had maybe one page of spacers in 1987 had entire sections by 1989. NASCAR took notice too. Cup Series crew chiefs started experimenting with spacers, finding they could tune engine characteristics by changing spacer height and internal design. By 1990, NASCAR had to create specific rules about spacer dimensions because teams were gaining significant advantages with creative designs. The irony? Many of these million-dollar race teams were using concepts discovered by a small-town racer working in his garage. The street performance market exploded. Hot rodders who had been struggling with throttle response issues on their carbureted engines suddenly had a solution. Edelbrock, Holley, and other aftermarket companies started producing spacers for every conceivable application. The 1-inch 4-hole tapered spacer became as common as chrome valve covers. Magazine articles about easy horsepower always included carburetor spacers in their lists. But the real revolution happened in Detroit's engineering departments. Morrison's discovery forced a fundamental reconsideration of intake manifold design. Engineers who had been focused on peak horsepower numbers started paying attention to part throttle operation. They realized that 99% of street driving happens at part throttle. Optimizing for that operating range, not just wide-open throttle, became the new priority. General Motors quietly incorporated spacer-derived concepts into their tuned port injection system for the 1985-1992 Corvette. Look at the TPI's intake design. It has a large plenum area that serves the same function as Morrison's spacer. The Vortec engines introduced in 1996 featured intake manifolds with increased plenum volume and smoother transitions. Even modern direct injection engines use principles Morrison discovered, giving the intake charge space to organize before entering the combustion chamber. The aftermarket responded aggressively. By 1990, companies were producing hundreds of different spacer designs: open plenums, divided plenums, burst panels, shear plates, each claimed to be the ultimate solution. Computer modeling and flow bench testing became standard development tools. What started as one man's intuition became a science. Universities started studying spacer effects in their engineering programs. SAE papers were published on intake charge motion enhancement through geometric optimization. Morrison himself never got rich from his innovation. He never patented the design, believing it was too simple to protect. "It's just a chunk of aluminum with some holes in it," he'd say. He continued racing at Highland Rim until 1994, winning 3 more track championships with increasingly sophisticated versions of his spacer design. He kept his day job at the tool and die shop, though he did start a small side business making custom spacers for local racers. The bigger players weren't so humble. Wilson Manifolds built a multi-million-dollar business largely on spacer technology. Their CNC machined spacers, based on computational fluid dynamics modeling, could cost $500 or more. Professional racing teams would spend thousands testing different spacer configurations for specific tracks. What Morrison had done with modeling clay and intuition, they did with supercomputers and wind tunnels. By 1995, the transformation was complete. Every serious performance intake manifold incorporated spacer-derived design elements. The aftermarket offered literally thousands of spacer options. Racing rulebooks had extensive regulations about spacer dimensions and configurations. What had been dismissed as a useless chunk of aluminum had become essential technology. The human element makes this story even more compelling. Michael Strasser, the GM engineer who initially mocked Morrison's spacer, became one of its biggest advocates within GM. He led the team that developed the Gen 3 small blocks cathedral port heads, which incorporated lessons learned from Morrison's discovery. In a 2010 interview, Strasser admitted, "Tommy Morrison taught us that sometimes the best engineering happens outside engineering departments. He reminded us to listen to the people actually using our products." Morrison's story spread through the racing community as legend. Young racers would seek him out for advice, and he always obliged. His philosophy was simple. Listen to your engine. Feel what it needs. The textbooks don't drive down the track. You do. He became a mentor to dozens of racers, teaching them not just about spacers, but about problem solving, about trusting their instincts, about not being intimidated by experts. The safety implications were significant too. Better throttle response meant more predictable handling. Drivers could modulate power more precisely, coming out of turns. This reduced accidents caused by sudden oversteer when the power hit unexpectedly. Several professional drivers credited spacer technology with making their cars safer to drive at the limit. Even the environmental impact was notable. Better fuel atomization and distribution meant more complete combustion. This reduced hydrocarbon emissions and improved fuel economy. The EPA actually cited improved intake design, partly derived from spacer technology, as a factor in meeting tightening emission standards in the 1990s. Morrison's chunk of aluminum was helping clean the air. Looking at modern automotive technology, Morrison's influence is everywhere. Variable intake manifolds that change runner length based on RPM. That's extending the spacer concept of optimizing airflow for different operating conditions. Tumble flaps that create swirl in the intake charge. That's sophisticating what Morrison's velocity stacks did. Even Tesla's electric motors use cooling passages designed with principles similar to Morrison's airflow management. The philosophical implications run deep. Morrison's discovery challenged the entire hierarchy of automotive engineering. It proved that innovation doesn't require million-dollar laboratories or advanced degrees. It showed that practical experience and intuitive understanding could trump theoretical knowledge. It demonstrated that sometimes the best solution is the simplest one. The racing world learned this lesson well. Today's Saturday night racers approach problems differently because of Morrison. They trust their instincts more. They're willing to try unconventional solutions. They understand that feeling, and hearing what their machines need is just as important as what the gauges say. Morrison didn't just improve their engines, he changed their mindset. The corporate world learned too, though perhaps more slowly. GM and other manufacturers started consulting with racers and mechanics more seriously. They established grassroots racing programs, not just for marketing, but for R&D. They recognized that innovation could come from anywhere, that sometimes a machinist in Tennessee understands airflow better than a PhD in Michigan. Morrison retired from racing in 2001 at age 56. His final race car, a fourth-generation Camaro, ran a sophisticated multi-piece billet spacer system he'd developed over 3 years. It made 487 horsepower from a 3-foot-8 cubic inch engine built with mostly stock parts. At his retirement party at Highland Rim Speedway, hundreds of racers showed up. Many brought their own spacer designs to show him, students proud to demonstrate what they'd learned from the master. In 2019, Morrison passed away at age 74. His obituary in the local paper mentioned his racing success, but not his engineering innovation. The racing community knew better. Online forums lit up with tributes. Professional engine builders shared stories of how Morrison's discovery had influenced their careers. Several NASCAR crew chiefs sent flowers. Wilson Manifolds named their newest spacer design the Morrison Series. Today, if you walk into any speed shop in America and ask for a carburetor spacer, you'll be shown dozens of options. The salesperson might not know the history, might not mention Tommy Morrison's name. But every one of those spacers carries his DNA. Every tapered transition, every velocity stack, every carefully calculated plenum volume traces back to that night in 1987 when a small-town racer decided to trust his instincts over expert opinion. The lesson transcends automotive technology. Morrison's story reminds us that innovation doesn't always come from where we expect. It teaches us that practical experience and theoretical knowledge need each other. It proves that sometimes the most profound discoveries are the simplest ones. It shows that challenging established expertise isn't arrogance if you've done your homework. Modern engineers study Morrison's approach in design thinking courses, not the spacer itself, but the methodology. Observe the problem, trust your instincts, test your hypothesis, iterate based on results. Don't be intimidated by conventional wisdom. It's a process that works whether you're designing spacecraft or solving everyday problems. The automotive aftermarket continues to evolve spacer technology. Companies now use 3D printing to prototype complex internal geometries impossible to machine conventionally. computational fluid dynamics software can simulate millions of design variations. But they're all chasing what Morrison found, with aluminum and intuition, the perfect management of airflow in transition. GM never officially acknowledged Morrison's contribution to their intake manifold development, but actions speak louder than words. Every GM Performance Parts catalog since 1990 has featured carburetor spacers. Their crate engines come with spacer-optimized intake manifolds. Their engineers now routinely test part throttle response as rigorously as peak power. The small-town racer had taught the giant corporation a lesson it couldn't ignore. Racing continues to be the proving ground for spacer innovation. Sprint car teams use spacers so tall they look like velocity stacks themselves. Drag racers tune their 60-foot times with spacer adjustments measured in 1/16 of an inch. Road racers select spacers based on track characteristics, shorter for tight courses, taller for high-speed circuits. Morrison's chunk of aluminum has become precision science. The democratization of performance is perhaps Morrison's greatest legacy. Before his discovery, serious horsepower required serious money. Factory-backed teams had insurmountable advantages. Morrison's spacer leveled the playing field. For $50 and some tuning knowledge, a privateer could compete with corporate teams. He didn't just improve engines, he improved access to performance. In the end, Tommy Big Red Morrison's story isn't just about a carburetor spacer. It's about the value of practical knowledge, the importance of questioning authority, and the power of simple solutions. It's about a working man who saw something experts missed and had the courage to pursue it. It's about innovation coming from unexpected places and the racing community's role as automotive R&D's guerrilla laboratory. Morrison once said, "I didn't outsmart GM. I just listened to what the engine was telling me. They were too busy talking to hear it." That humility characterized him, but history suggests otherwise. He did outsmart GM, not through superior resources or education, but through observation, intuition, and relentless iteration. He proved that sometimes the best engineer is the one with grease under their fingernails. What's the most innovative solution you've seen come from unexpected places? Have you ever solved a problem experts said couldn't be fixed? Share your stories in the comments below. And if you enjoyed learning about how one racer changed automotive history with a simple piece of aluminum, make sure to subscribe for more stories of unlikely innovations that changed entire industries. Because sometimes the biggest breakthroughs come from the smallest shops. And the next Tommy Morrison might be in your local garage right now, solving problems the experts don't even know exist yet.